Hey folks, this is Captain Jones here to talk to you about memory mapped input version 1. Today we're going to talk about what memory mapped input is, and one objective we have is for you to be able to describe the circuit that allows the LC3 to read from an input device by acting like it's reading from a memory location. And then once we know that, we'll hopefully arm you with the information to be able to write short assembly programs that read from memory mapped input devices, which account for something called synchronization, which we'll look at in just a second. So let's get started. Okay, so here is our model of the computer. We're going to look at this box here, our input. How do we get input from some external device into our computer? And we're going to assume that it's memory mapped, which means that somewhere in our memory, from 0 to FFFF, are registers that we, or places in memory that we can read from and can control in order to get information from an input device. So I've got a very poorly drawn keyboard here, which we'll assume has 8 lines that connect to the LC3, and those 8 lines report the ASCII value of whatever key is currently being pressed on the keyboard. And so we're gonna assume our input device, or we're gonna design an input device that has two places in memory that read those values and control that device. So that's the KBSR and KBDR, which are the keyboard status register and the keyboard data register. And so those 2 spots in memory look like this. The keyboard data register, we can imagine, has almost a direct connection to the keyboard, such that whenever a key is pressed, the lower 8 bits are just automatically changed to the ASCII value that's being pressed on the keyboard. And right now, KBSR, the status register, has just 1 bit that is of interest to us, which is the bit 15. That we'll call the new bit. This bit is set to 1 whenever there is new data in the data register. And so you can, we could potentially, as long as this is set up correctly, we could use this very simply, like you can see here in this little code snippet, to read values from the keyboard. So if we could either use the address directly, FE02, and load a register with whatever values in there. So then the lower 8 bits in R0 would be whatever ASCII value is currently being pressed on the keyboard. Or in some, equivalently, we might use the load indirect instruction if we want to make KBDR a mnemonic for that address, and then we could load indirectly from this address, and this will accomplish the same thing. It'll take whatever value is here in memory, whatever ASCII value is being pressed by the keyboard, and load it into R0. Okay, so before we look at some more complicated programs, let's stop and ask, okay, what do we mean? How in the world does this keyboard actually connect to memory? And so what we have to kind of do is broaden our understanding of this thing called memory. So we have this abstraction where we've got a block of values, 65,000 or so, and 2 of them somehow control inputs and outputs. And what that actually looks like in memory is, what that actually looks like in implementation is, as you can see down here, where this thing that we call memory is actually a conglomeration of a couple of different pieces of logic. There is one, big device in here, which is the literal memory. This is where we, store our programs, and we, read and write data and those sorts of things. But then we have some extra stuff around it. That makes the combined thing act as though we had these two devices here, the KBSR and KBDR, in this memory space. So in order to accomplish that, what we need to do is, number one, we have the KBSR and KBDR as sort of pieces of logic that are separate and right next to the actual big memory device. And so not shown here, but you can imagine that this KBDR, this is a set of maybe it's D flip-flops or whatever, that is very literally connected to this keyboard here. And there might be some external logic that we're not quite showing, which just makes sure that this represents new values every time the keyboard is pressed. We've got a block here called the address control logic, which reads from the memory address register, and this is a block which knows that KBSR and KBDR are located at these two places in memory, FE00 and FE02. So this device is responsible for reading this register. Reading this memory address. If that memory address is something like FE00, then it knows to sort of not turn memory on. And instead to turn on, so to speak, KBSR, because the address of KBSR is FE00. In this case, we are only concerned about reading from this device. So if the memory address is either FE00 or FE02, then we're doing a read. So the memory data register is being loaded from something. And so the address control logic has this multiplexer down here called INMUX, which can select the data register to be loaded either from normal memory, if we've got pretty much any other address, or specifically the keyboard status register if the address in the memory address register is FE00, or the keyboard data register if the address in the memory address register is FE02. So by combining our big block of memory with our programs and our data, with some logic that connects more directly to our input device, our keyboard, and adding some control logic that can control whether reads and writes go to this device or this device, we can take these together and kind of imagine them, abstract them as if they were a big piece of memory device. And now instructions in the LC3 that read from these two memory locations effectively read from our input device. Okay, so when we got a program like this, we're not necessarily reading from our data memory. What we're doing is we're telling the address control logic that we want to access one of these two registers, and so we can read from the data register in that way. Now, when we do that, we get two complications. Number one, let's take a look at this piece of program, this little code snippet, where we are reading from the data register into R0, and let's assume that in this case R0 gets the ASCII value for lowercase e. Let's assume roughly a second passes, some amount of time. We load into the R0 again, and R0 still has the value lowercase e. The question becomes: is this the same lowercase e that was in the data register a second ago, or is this a different e? There's lots of words in the English language that have two e's next to each other, right? So how do we figure out which is which? Is it the same or is it different? And so this is the solution to this is something called handshaking or synchronization. And so because the input device doesn't adhere to the same clock that's running the LC3, input can come in at any time, then we need some way to sort of synchronize these two things together. That is, we need to synchronize the information that's in the keyboard data register with our understanding of kind of what's in there. And so in addition to these two registers kind of interfacing with our input device, we have a couple assumptions about how they work. Namely that whenever we write to the keyboard data register, so whenever someone presses a new key on the keyboard, that will set bit 15 in the status register. Recall that was the bit here that indicated that there was new data in the keyboard data register. And furthermore, we'll assume that there's some external logic such that whenever the processor reads from the data register, that will clear bit 15. So as soon as there's a new character here, this bit is set. As soon as we read it, that bit is cleared. So in this case, for example, we could check that status bit. If we in this first read would clear that status bit. If we got to this line of code here and that bit was still cleared, then we would know, okay, no new data has been written to the data register. However, if that status bit was a 1, we would know that, okay, these were two different e's because we read one e, and since then a new piece of data has been written to the keyboard data register, and even though it's the same character, that's effectively a new piece of information. Furthermore, we'll make the assumption that that any attempt to write to the keyboard data register is sort of silently rejected if the bit 15 in the status register is 1. So that means if there's an ASCII value written to the data register and the keyboard status register indicates a 1 in this position. If before we can get around to reading the data register, the typist is typing more characters, they're all sort of silently rejected. We'll only get the first one that filled the register since the last time we read it. And so what that means, like I said before, is that before we actually read from the data register, we want to check the status register to see if there's actually a new character in there. So in this second example, we're going to load the data register into R0. Let's say it gets at lowercase e. 1 second passes again. Now, instead of just reading it directly, the first thing we're going to do is load R0 with the value in the status register. All right. If the status register has a 1 in this position, you can imagine this or a number. You can imagine this would be the bit that would indicate if this unsigned integer were negative. Then if it's, or let's do this the other way around. So if there's a 0 here, meaning there's no new data, then you can imagine whatever values in this register could be interpreted as either 0 or a positive number, because there's a 0 in the most significant bit position. So if it's 0 or positive, that means there's no new information. So in this case, we're going to branch to this code called same, and that's just going to skip over reading the data register. We're going to execute some other code. But if the bit 15 is set, so if there is new data, and this looks like a negative number, we are not going to execute this branch. That's when we know we can load from the data register into R0 again, and whatever value we have is it's a different value. It's a new piece of information. So I mentioned that there were two complications. Number one was this handshaking or the synchronization piece, which helps us figure out whether or not we're looking at new information. Number two is kind of a to be continued. This is the difference between two things called polling and interrupts. So this code is an example of polling, meaning that we are sort of manually inserting into the code checks if checks for new data. There are advantages and disadvantages to that. A big disadvantage you might imagine is, if it takes me a full second to read from the data register, you can imagine that any normal typist has already typed many characters. So we would, if we were truly reading stuff from the keyboard, we would need this to execute much faster than this. And so we'll look at a future lesson. How interrupts can kind of help us solve that problem and to compare these two a little more fully. Okay, so today we looked at memory mapped input version 1, and we said that the concept is that we have some spaces in memory which are connected to an input device, in this case a keyboard, such that whenever someone is pressing a key on a keyboard, that value is being loaded into this spot in memory called the keyboard data register. And anytime we have a new piece of data in that register, this bit here in the keyboard status register gets set. And so in actuality, we can pretend that these are memory locations, then read and write to them using our memory instructions like load and store. In reality, to actually do that, we have our logic surrounding our actual memory block. These are not, there's not like stuff sort of tucked in memory that's controlling this input device. There are separate pieces of logic here that are connected to this keyboard, which we call the status register in the data register, and then a piece of control logic, which can identify when we are reading from these two locations, and control the memory to say, hey, this is not you, and put the correct value in this multiplexer so that the data register gets the correct value from one of these two registers, if that's what we're reading from. And if you sort of look at everything in this green box together, it looks like this abstraction over here. I can just read and write from any memory address from 0 to FFFF, and if it's these two, FE00 or FE02, I get the status register and the data register. So I can put everything in this green box as sort of a nice abstract conceptualization as one big block of memory, even though part of it is allowing me to access the input device. And so, reading from the input device just involves, or in this case, as simple as reading the keyboard data register. But in order to make sure that I'm not rereading the same value, I need to concern myself with this idea of handshaking or synchronization. So that's the purpose of this status register, and there's kind of an implicit, assumption in using this input device as to how the status register, the new bit gets set, and when it's cleared. That helps me figure out if there's new data in my register. This process of checking the status register over and over again, you can imagine this in sort of a loop to see if there are new characters, is something called polling. I'm actively or manually polling the status register to see if there's a new value in there. And we'll look at a little later a slightly more efficient way to do that via interrupts. All right, folks, that's all I got. I'll see you next time.